Okay, for the first two slides of this, I do not need you to write anything down, but I'll have you have some quick discussions with your table groups. And so my first slide, you don't have to write anything down for this, is just if you were solving sine theta equals 1/2 from the unit circle, so think about things we did in chapter 4, that would be in the range 0 to 2 pi, where we include 0 but not 2 pi. What would your solutions be for this equation? So have a discussion with the people at your table groups. What would your answers be for theta? Okay, Allie, did your group talk about some solutions to theta? Pi over 6, which is 30 degrees. And is that the only solution on the unit circle? Oh, 5 pi over 6 is also a solution. So I have those visually here for us. Remember that on the unit circle, sine is equal to the y-coordinate. So we're thinking about those ordered pairs as we go around the unit circle. Where is the y-coordinate equal to 1/2? That would occur in quadrant 1 and quadrant 2, okay, where the y value is positive. So the pi over 6 and the 5 pi over 6. We'd have two answers. Okay. Now, are those the only angles that have sines of 1/2? Not if we eliminate this restriction that it has to be on the unit circle from 0 to 2 pi. So can you give me an example or a way to find another angle that has a sine of 1/2? A coterminal angle, right? I mean, technically, the angles that have sine of 1/2 have to be those same two angles in quadrant 1 and quadrant 2, correct? It's got to be in the same location, so we're using the same reference triangle, 30 degrees, and we're calculating sine, y over r the same way, and we're still getting 1/2. But Emily brought up a great thing. What about all of the coterminal angles? So when you're looking for solutions on the unit circle, you know, you're restricted in that range from 0 to 2 pi, but if we don't restrict ourselves to that range, we're really looking at solutions more like from the graph. So again, you don't have to write anything down here, but we talked about in chapter 4 how the graph of sine is this continuous wave. It's a periodic function, so the graph has a period, which means it's one cycle that just repeats over and over again. Well, if that cycle continually repeats, then those angles keep showing up where sine is equal to 1/2. So there are two angles marked here, right here. This is x equals pi over 6 and x equals 5 pi over 6. And they're showing you that those are the values where y is equal to 1/2. But when you look at it more in the function that we graph, you can see that if you drew a horizontal line through y equals 1/2, there are infinitely many solutions where y is going to be 1/2, and that will continue on further. So what this slide, and you can see this picture in your textbook if you want to look at it later, is it shows these are the original solutions on the unit circle. To get other angles, you're using the topic that Emily brought up, which is this idea of a coterminal angle. So to the right there, we're adding 2 pi. If we just add a full revolution, we're right back at the same angle, and we have the same sine value. So pi over 6 plus 2 pi, 5 pi over 6 plus 2 pi produces other angles that have the same sine value. And at the same time, I could subtract 2 pi. And then I could also do things like add more 2 pi's or subtract more 2 pi's. So we understand that if we release the limitations of it has to be on the unit circle, there are infinitely many solutions that work. So that's going to be something that pops up in our work when we are solving trig equations today. Before we get into some examples, we'll write down a few tips and pointers for us. You can go back and read these as you're working on your homework over the weekend or preparing for quizzes and tests. So first thing, our goal to solve a trig equation is obviously to solve for like x or theta to get that variable all by itself. In order for us to be able to do that, we're going to have to isolate the trig function first. It's a lot like solving a logarithmic equation. We're going to get the log by itself and then rewrite it in exponential form. Well, we want to get the trig function all by itself first. Things that you might do would be combine like terms. Now, this could be combining like terms like numbers, but note that we can also have like terms that are trig functions. So a cosine of x can combine with other cosines of x. A sine squared x can combine with other sine squared x's. So if you see more than one of a certain term, try to combine them. You might also utilize factoring. So we know from semester 1 and algebra 2 that sometimes if you, like in algebra 2, if you have x squared and x, you can't solve that by like regular reverse PEMDAS. You're going to need to at some point factor it so that you can set your factors equal to 0 and solve. So that might be true if we have different types of trig functions there. You can also use substitution with trig identities. This is going to be less common for us in our homework over the weekend. But if you ever got to an equation where there was more than one trig function, you might think about rewriting it or using some of your trig identities to help you with that. Now, the other thing that I'll say is make sure that you include the complete solution. So if the directions on the homework or the directions on your quiz or the directions on your test don't tell you to give me answers between 0 and 2 pi, then you must include the full solution, which is the angle, the answer, plus the period times n. So I put period in parentheses and n on the outside. That'd be times multiplication. You know, if we're working with sines and cosines, our periods would be 2 pi. If we're working with tangents, we would take a pi. Okay. N is going to represent an integer. Which represents how many revolutions you are adding or subtracting. Okay, so that gives us those coterminal angles, and n will just be left as a variable. Now, if the directions specify that your angle solution should be between 0 and 2 pi, would you write your answer like this? No, because then you would be including things outside of that range. So read the directions and give the appropriate answer based on what it's asking. Okay, so now we'll do some examples. Here's our first one. Solve the equation. The cosine of x minus the square root of 3 is equal to negative cosine x. I'm going to give you about 30 seconds to brainstorm with your tables what you might do to get started to solve. See what are some ideas that you or your classmates have. 30 seconds, go. Okay, 30 seconds is up. Catherine, I'm going to ask your group come up with any ideas. Okay, move cosines from one side to the other because you have a cosine on the left and a cosine on the right. In order to be able to solve, you really want to have one cosine, right? And you said subtract, so let's go ahead and subtract the cosine on the left to the right side. I like that. Because if you're thinking ahead to the rest of the process, you want to isolate the trig function, so you'd really like cosine to be on the other side of the equation from the square root of 3. So that leaves me with negative square root of 3 equals negative 2 cosine x. And David, do you have a next step that we could do right there? We still got to get the cosine all by itself by negative 1 or negative 2. That'll kind of kill two birds with one stone. If we divide by negative 2, then negative divided by negative becomes a positive. We got square root of 3 over 2, which you should feel pretty good. That's from the unit circle, right? Equals the cosine of x. Can you now answer that question? What angles have cosines of square root of 3 over 2? Pi over 6, 11 pi over 6. So this, we're going back to naming the angles from the unit circle as opposed to, like, remember when we were doing inverse trig functions, arc sine, arc cosine, where we were like restricted in those ranges. We don't have to worry about that anymore. And then because it doesn't tell me that my answers are limited, I know that these are not the only angles where this will happen. I've got to add my complete solution set. Since it's a cosine, the period is 2 pi. So I'd say plus 2 pi n plus 2 pi n. And n could be anything. N could be negative 5. That means I'm going to subtract 5 revolutions, whatever that gives me, that has the same cosine value, square root of 3 over 2, whatever that angle is. Okay, so here's our complete solution on the right side. Are we okay with this so far? Does anybody have any questions or clarifications we should make? No? You're good. Okay. Thumbs up. Okay, try another one. Cosecant of 2x minus 2 over square root of 3 equals 0. And again, I'm going to give you an opportunity before we solve it on the board to kind of think out loud with your group and throw some ideas out and hear some different ways of thinking about it. Because I would say there's kind of different steps for different people. But I'll give you about 30 seconds again. Go ahead and have a table group conversation. What would you do here? How would you solve it? What would happen? Go. No, it is not. Can you? Okay, our 30 seconds is up. Kirsten, did the group talk about anything that would be helpful?
We added 2 over 3.
Yeah, we want to isolate the trig function. You could add 2 over square root 3 to the other side. How many groups did that? Raise your hand if your group did that. Oh, every group did that. So what did you do after that? Oh, Bruin, share with us. Okay, definitely. So some people are looking at this and they don't like the fact that it's unrationalized because we're always saying rationalize, rationalize, rationalize. So if you wanted to, you could rationalize it, okay? Does it really change anything about solving it to rationalize it? No, it just shows you another way to write it, okay? So you could rationalize it. I don't think that step is necessarily required to solve. Did anybody do something else besides rationalize it? I'm going to be real honest. I don't prefer cosecant. What do I prefer? Sine. In my head, I know the unit circle, and I know sine, cosine, and tangent really well in the unit circle. So you could do what Bruin does, which is rationalize it. It looks more like our answers for cosecant, secant on the unit circle now because we were always rationalizing them. But the other thing you could do if you wanted to is, if I'm asking you to solve the equation cosecant of 2x equals 2 over square root 3, I'm also asking you to solve the equation sine of 2x equals square root 3 over 2. Okay. Now, either one of those is acceptable, okay, because Bruin can think about what the sine would have to be and what angle so that cosecant was 2 square root 3 over 3. Okay. But I'm going to say, like, I probably prefer to think about sines. Okay, so I'm thinking, yeah, sine would be easier for me to do. I know what angles have sine square root 3 over 2. Now, there has been a question in some of the different groups, and I heard different conversations about the 2 with the x. Are you allowed to divide that right away? No. Okay, it's trapped inside the trig function. Means you're going to have to wait to do anything with the 2 until you're done solving. So at this point, at any one of these 3 lines that we have written, where we added it to the other side, where Bruin rationalizes the denominator, or where I rewrite it as sine, we're ready to say what 2x is equal to. Okay, what angles have cosecants of 2 over square root 3, or 2 square root 3 over 3, or in another sense, have sines of square root 3 over 2? What are those angles on the unit circle? 60 degrees, which is pi over 3, or 2 pi over 3, because it would have to be in the second quadrant. Okay. Now, what I usually do on these is I just go ahead and I go back, like, it's sine or it's cosecant. What are the periods for sine and cosecant? 2 pi. So I'll just tack on to that pi over 3 plus 2 pi n plus 2 pi n. Okay, so that setup is still the same, but what's really important is it's not just x equals, it's 2x equals. So you still have one other step to do, which would be divide by 2 or multiply by 1/2. Okay, since I have, with radians, I usually have fractions. I usually just go ahead and multiply by 1/2. Now, I'm multiplying the whole solution by 1/2. Okay, so the 1/2 times 2x gives me x. The 1/2 times pi over 3 gives me pi over 6. And then 1/2 times 2 pi n is just pi n. And I do the same thing for the second solution. Distribute that 1/2 through everything. 1/2 times 2x is x. 1/2 times 2 pi over 3, the 2's are going to cancel out, so it's going to be pi over 3. And then plus pi n. Now, what's interesting about that as well, think about the original problem right up here, where we have the cosecant of 2x, and then think back to our section on graphing. What is really the period of that function, cosecant of 2x? Someone said it? Pi, because the period is 2 pi divided by b, where the 2 times x is representing the b. So 2 pi over 2 would be pi. And see how that really is showing up right here if I distribute the 1/2. Okay. So you wouldn't have to put 2 pi n right here. You could do it at the end and think about the period of the original function. But I usually just add the plus 2 pi n always and then just distribute that piece. Okay, and that'll give me my period that I want to add. Any questions on that example that you want to talk about? Okay. Find all the solutions of the equation in the interval from 0 to 2 pi for the equation 2 cosine squared x equals cosine x. And I will have you check really quickly with your small groups. What would you maybe do to solve? What are some options that you have? We'll share out here in just a moment. 30 seconds right now. Okay, Ethan, do your group have any suggestions for us?
Okay, well, you can subtract cosine x from the right side.
Good. Subtract the cosine x, get the cosines on the same side.
And then factor out cosine.
Factor out cosine. Right, these are not like terms, so I won't be able to group them together. So factor out a cosine. I'm left with cosine x times 2 cosine x minus 1 equals 0. And then when you factor, set your factors equal to 0. So now you're really solving 2 equations instead of 1 equation. Okay. So we're going to solve cosine of x equals 0. We're also going to solve 2 cosine of x minus 1 equals 0.
So she gave 4 answers.
Yep, 4 answers. And we've got to pay attention to here on this one, we don't want all the answers, right? We want only the answers from 0 to 2 pi. So we will have 2 for cosine x equals 0. We will have 2 for the other equation. Okay, do we know where cosine is equal to 0 on the unit circle? What angles? Pi over 2? 3 pi over 2. Both of those are between 0 and 2 pi, so those are my solutions for the first factor. And on the second factor, I'd have to add 1, divide by 2, so I'm doing cosine is equal to 1/2. Those angles are pi over 3 and 5 pi over 3. In order for cosine to be positive, we must be in quadrant 1 and quadrant 4, because that's the x value, so we're going to the right. Okay. So we'd pick the pi over 3 angle in quadrant 1 and then 5 pi over 3 in quadrant 4. Okay, we have our answers. No plus 2 pi n's because we don't want all the answers. Okay. Okay. Any questions there? Okay, the next example we'll do really quickly. I'll try to walk you through, and we won't spend a whole lot of time. This is just another example where, you know, when you look at it, 2 cosine squared x minus 5 cosine x plus 2 equals 0. What are we going to have to do in order to be able to solve this guy? Factor it. And this one's factor a trinomial, so now you see like factoring in 5, 1. It's important that we could do that. So I would set up 2 groups of parentheses. In order to get that first term of 2 cosine squared, I must be multiplying a 2 cosine x and a cosine x. To get the last term of plus 2, I must be multiplying 2 and 1. And so you just have to think carefully about where you're going to put the 2 and the 1 in the last places so that you get your middle term of 5. Should be 1 and 2. So that I get 4 cosine x and 1 cosine x for outsides and insides. And in order for it to be negative, they should both be negative. That will still give me a positive 2 at the end. So factor trinomial. Then set your 2 factors equal to 0. This first one is going to be the one that we just did, right? Cosine x equals 1/2. So we're going to say pi over 3 and 5 pi over 3 again. Okay, so we just did that. And you're going to see, like, as you work through these problems, because we're going back to the unit circle, there's only so many answers that you're going to be able to produce, or so many numbers that you're going to see, because they have to be values on the unit circle. When you solve the second one, cosine x minus 2 equals 0, What angles have cosines of 2? None of them. So, no solution here. On the unit circle, there is no angle that has cosine of 2. We know that that's really outside the range of cosine. If you think of the graph of cosine, the graph of cosine's parent function goes from -1 to +1. So 2 is outside of that range. Okay, there is no solution. Okay, last one that we want to look at. But your cosine, your ratio, so change the radius is a great question. If your radius was 2, could your cosine be larger? Remember, cosine is the ratio of the adjacent to the hypotenuse. In order for that ratio, adjacent over hypotenuse, to be 2, it would mean the adjacent side is twice the length of the hypotenuse. Hypotenuse is the longest side of a right triangle. So, by definition of what the ratio of cosine is, adjacent to hypotenuse, it can't ever be more than 1 or -1, even if we make the radius bigger. The highest ratio is going to be 1. Our last example is 3 tangent cubed x equals tangent x. I do want you to kind of think out some steps with your groups here in just a moment, so I'll give you some time to jot this down. We are solving to find all the solutions for the equation in the interval 0 to 2 pi. And we've got 3 tangent cubed x equals tangent x. And have that conversation about 30 seconds with your groups. What would be some steps you would take to solve? Okay, walk me through some steps. What are we going to do? Just shout them out. Sooner you tell me, the sooner you do your homework. Bring the tangent over. 3 tangent cubed x minus tangent x equals 0. I get the tangents on both sides. Factor out a tangent. You know, the tangent cube should make you a little concerned. Okay, so factor out both sides, or factor tangent out of both. Set them equal to 0, Blake says. So tangent x is equal to 0. 3 tangent squared x minus 1 is equal to 0. Oh, how'd you get that? Okay. Add 1, divide by 3, so that gets us 1/3 on the other side. And you should be a little bit worried there. You're like, wait a minute, 1/3 is not a tangent value on the unit circle, right? But that's tangent squared, so you have to square root both sides. And when you square root 1/3, it's like the square root of 1 over the square root of 3, which is 1 over the square root of 3, which is, like David was saying, square root of 3 over 3. Okay, so I did a little bit of work right there. Some of us might not need to do that work. We would know that it would be square root of 3 over 3. So what does your next line look like? Tangent x equals just square root of 3 over 3? Is that what my next line looks like? Sure. So we have the equation x squared equals 4. The answer is x equals 2. Anytime you take a square root to solve, you better add the plus or minus. We don't know if it was positive times positive or negative times negative, so we're back in algebra. And we have to include all the solutions there. So anytime you have a squared trig function, you're going to have a plus or minus, which means when you're thinking about angles that have tangents of that value on the unit circle, you're really thinking about all those angles in all the quadrants, right? Okay, so what angles have square root 3 over 3 or negative square root 3 over 3? Pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. That pi over 6 family. Okay, it's going to give us 4 answers for that one factor. And what angles have tangents of 0? 2 pi and pi, but we're going to write 0 and pi, because if you look back at our directions, 0 is inclusive, 2 pi is exclusive. Now, I probably won't take off if you say 2 pi, because like technically that is the solution. But just know that like if you're checking your answer in the back of the book is always, if it's on that range, it's always going to say 0 instead. Okay, great work. So the next thing that we're going to do is you do have a homework assignment. It's on your gold sheet. And you can get out your textbook if you want for that. I'm also going to be passing out your quizzes. And so here are some directions for quiz correction.